Hello, everyone. Can everyone hear me? Okay, great. We're going to get started. Well, thank you, everyone, for coming tonight. My name is Megan Monig. I'm the Curator of Education and Public Programs here. Thanks to the generous support from the Homer Foundation, we are hosting a lecture series over the next couple months, focusing on the impacts of climate change. And to start this lecture series, we have Dr. Higman here this evening presenting his lecture titled The Bear's Dilemma, with time for questions at the end, so thank you. And then I also wanted to let everyone know next Friday at 5 p.m., Ka'alangan Elder Mentor Piama R. Olier will be presenting the second lecture of this series. That is in conjunction with our temporary exhibit upstairs, Bearing Sea Storms Past to Present. And all right, thank you everyone again, and here's Dr. Higman. Thank you.
Thank you. I'm going to put my phone over here just so that I have some sense in case I get really rambling that I should probably speed up. I really appreciate you all being here. I'll be talking a lot about landslides tonight and trying to dive into a topic around deep-seated landslides, really large landslides, and especially those that are related to climate change. And I think this is an important topic. It's got me really worried. I worry that for Alaska, landslides might be like what hurricanes have been for Florida and wildfires have been for California. They may pose existential risks to our communities, and that they might have huge impacts on our economy. But in order to really dive into that, I want to spend quite a bit of time on context, on trying to understand how whatever science I might present to you here, how that might actually be useful, because I think this is a really difficult problem. And I see with professionals, like I can kind of call myself a professional studying natural hazards, I think we often just kind of assume that if we do this stuff, then it's going to work out well. But I think when we examine how things work out, that's often not the case. So my kind of funny title here, I actually commissioned my daughter, Latuya. This is her first commission artwork right here. She's 14. And the inspiration for this, actually a local Homer, a pillar of the community, Bob Shavelson, and I were chatting, and I was talking about how challenging some of these natural hazard mitigation problems are. And he said, humans are notoriously bad at mitigating natural hazards. And I thought that was really interesting. I was trying to picture, what's this table? There's the human sitting there. Who else is around that table that's pointing at the human being like, wow, that one is really bad at mitigating natural hazards? And so we'll explore a little bit through the course of this how bears might do at this in comparison to humans. You can see here this bear struggling with this decision here between a salmon and a probabilistic hazard map. And I don't want to spoil anything, so I won't give you my speculation of how the bear might choose in this situation. But we can start right off with a little bit of how humans choose faced with similar choices to make. There have been a number of cases in southeast Alaska where hazard maps have been published as far as landslides, and they actually have been rejected by local public officials. I don't think any salmon bribery was involved in these decisions. I think this was, a different kind of decision. So this kind of illustrates as a starting point, this is not necessarily straightforward. Just going out and making a hazard map is not necessarily addressing this challenge. And I'm going to go back a little bit to review some things I presented here in Homer, actually a little less than a year ago, in a previous presentation called Cassandra and the Tortoise, because this is a really important foundation for what I'm going to be talking about today. And so one of the things that I looked at was how the 1964 earthquake is the start of an arc of scientists trying to address a natural hazard. This is one particular kind of earthquake called a Great Subduction Zone earthquake. They're the largest earthquakes that happen, to our knowledge, on planet Earth, I guess aside from like huge meteor impacts or something. And it was a devastating event for us here in Alaska, but it also was a really important part of starting to understand how these disasters unfold. And it was actually the basis for work that went on for 40 years. So we didn't have another Great Subduction Zone earthquake for 40 years after 1964. my friend and mentor, Brian Atwater, a giant in the field of paleoseismology, studying ancient earthquakes, spent a large part of his career studying these things and trying to figure out where they are. Here he's standing amongst cedars that were killed by an earthquake like this in 1700 in Cascadia, so along the Oregon-Washington coast. And so all of this effort was to try to reduce the impact of these disasters. And then after those 40 years, we got our first test in the Indian Ocean when a huge subduction zone earthquake struck Sumatra and the Andaman and Nicobar Islands. Produced a tsunami. Over 200,000 people died over the course of December 26, 2004. And looking back, the science didn't really do them much good. Now, you could make some excuses. This is a little bit of a blind spot for hazard mitigation. There aren't any big academic universities that were right in this area. We were working on it. We would do much better maybe if we went somewhere where actually for generations people had been specifically trying to understand this natural hazard. And it turned out that just 7 years later in Japan, we got to see that experiment. And this is a picture showing a tsunami from a great subduction zone earthquake pouring over a seawall in Miyako that was built specifically for the purpose of not being overtopped by a tsunami like this. So that's pretty disappointing to see, and this was a really, really devastating earthquake. Now, I'm maybe being a little bit overly negative about the success of science in addressing these, because in Japan, actually, that seawall ideally wouldn't have been overtopped, but it still slowed the wave down. It reduced the destruction. It gave people more time to evacuate. But it's still very, very disappointing as someone who studies these things to see all of this effort, when it's put to the test, perform so much more poorly than we might fantasize. Now, if you look back to the 2004 earthquake, there are a few bright spots. I was actually in this town, the town of Langi. We were there a few months after the tsunami in 2004. And my colleague Brian McAdoo actually wrote a whole paper on this village and what happened here. So within 10 minutes of the earthquake, there was 35 feet of water throughout town, and every building was destroyed. That building you see there was built afterwards. However, everyone survived. Every single person in town was up on the hill behind town by the time that tsunami arrived. And if you can imagine, 10 minutes between shaking starts and everyone is out of the zone of inundation for this really devastating tsunami. That is not just I think I know what to do when the earth starts shaking. This means a very deep engagement by everyone in that community. They're making sure everyone who has any trouble moving, all the little kids, everyone is up that hill, and not very much time at all. That's an incredible result, really, and it shows a very deep cultural commitment to preparing for that disaster. And another really cool story is the story of Tilly Smith. She was a British schoolgirl who had just had a lesson in tsunamis, and she was vacationing with her family in Thailand. She recognized early signs of the tsunami, managed to convince her parents, who then convinced others at the beach to evacuate, and they evacuated just ahead of the tsunami. No one died at that beach, which definitely can't be said for other beaches in the area. And so these are both examples of cultural mitigation of natural hazards, and they really show how human cultures can sometimes, really kind of embrace this effort to deal with these hazards. And so this was kind of one of the things I wanted people to take home from this presentation I gave before. I've actually started thinking about the work I do, studying these disasters and giving presentations like this as sort of a cultural activity in and of itself, like art or sports, rather than somehow separated off as a scientist. So, I might even say I'm really trying to pursue greatness, just like Timothy Chalamet, if anyone's been following the news lately. So yeah, does this distinguish us from the bears? How do the bears fare in this sort of thing? Well, bears also have cultures of hazard mitigation. They teach their cubs, they teach their young, just like Tilly Smith was taught, about hazards, and they communicate this between each other. I think some of the places where we can see this most clearly is places where bears are afraid of humans, because then we really get to see how they respond to this. So if you go to Brooks Camp, you'll see bears that will ignore a huge crowd of people just a few dozen steps away. Those exact same bears, the same individual bears, if they encounter a person somewhere elsewhere, they will run away right away because they know that humans can be really dangerous in that circumstance. So they have very complex thoughts about hazard mitigation. They even have fixed infrastructure like dens and stuff. They migrate to get out of areas that are dangerous. So that sort of cultural behavior, I think, is really a big part of bears as well. And if we look around at the different, our fellow species on this planet, it's not true for all of them. On the left here, this is a glacier mouse, which isn't a mouse at all. It's just a ball of moss that rolls around on a glacier and always growing up, but it rolls over a lot, so it grows spherically. As far as I know, they do not worry about the fact that at any moment they could blow into a crevasse or a moulin. Here in the middle, these are spruce trees growing on a moraine that's eroding into the ocean. So you've got both melting ice underneath them and the eroding coast kind of vying for the chance to tear their roots apart and kill the tree. Now these trees, as far as I can tell, do not band together, pool their resources, and hire spruce tree engineers to build barriers to coastal erosion. I think a lot about this marmot here on the right. I encountered her while I was along the Gulf of Alaska coast. She's living on this big coastal moraine. And it turns out this is an area I've done some science, some research in, and there is a lake up in the mountains far from where she lives, miles away. But it's perched, blocked from this area by a glacier that's rapidly thinning. And at some point, there's going to be this huge flood that's going to wash away much of this moraine. And so when I walked past this marmot, I knew that, and it actually didn't occur to me at the time to pause and talk to her about it and say, you might want to put some plans in place, how you would evacuate, what kind of precursory signs you might see that things were going bad. My instinct on it is that she wouldn't have really been very interested in the conversation. I don't know that she's anti-science. I think she just has other things that she would like to work and think about. So that's fine for some species, but both us and bears, we have this culture of hazard mitigation, or we have cultures of hazard mitigation. And part of what I wanted to grapple with here is this particular question of science. So if you look at my subtitle there, can we use science to prepare for climate disasters, to prepare for any natural disaster? And so this is kind of this quest we might go on, right? And try to use science, because I really don't think bears actually use science as we usually conceive of it. They might do some kind of hypothesis testing, but they don't systematically eliminate different variables. They don't look at the implications of their mathematical estimation of some natural process. These things are things that are pretty uniquely human, and we might actually do really well if we did manage to employ these, and it would be something that the bears don't have. It's this use of science that lets us understand the relationship between climate change and landslides. Now, it's not, our understanding of climate change isn't purely a scientific thing. It's actually the indigenous people in northern Alaska and such were ahead of the scientists in identifying the effects of climate change starting to become apparent. However, it's through that science that we're able to see the link to our burning of fossil fuels and to estimate future changes with very impressive accuracy. And it also allows us to figure out things like, okay, when the atmosphere is warmer, it carries more moisture, and so it's more likely that you'll get extreme rain. This is a number one driver, basically, for landslides. Glaciers, as things get warmer and they thin, they remove the pressure they put on mountainsides, and sometimes those mountains rely on that pressure to stay up so they can fall down. Permafrost is sometimes an important part of the strength of slopes, and so as it warms up, as it thaws, slopes can fail. We can actually look at an example. This is a model that I'm going to show you, a scientific model. It's quite simple. Interestingly enough, I would say this is one that is really an active area of debate amongst my own colleagues who are trying to understand landslides. So it's very simple, but it actually gets right out there to the cutting edge of science. And so it starts with the assertion that most times when you see mountains, there's probably uplift going on. So the mountains are actually rising upward. And actually, when we measure this sort of thing, we find that the mountains aren't nearly as high as the amount of uplift there's been. Like if it was just, oh, you took something, you lifted up, these mountains would be far, far higher than they are, and that's because they're eroding. And in fact, this erosion and this uplift seem to come into balance over time. So this is an equilibrium process. It's two things that are pointing in opposite directions, and the result is that there's not much apparent change over time, even though there's activity on both of these. And so you can ask, like, if you change something about the system, how does this landscape that was in equilibrium respond? So let's say we increase the amount of precipitation. Well, first of all, there's more water in the river. The river's potentially then going to erode more efficiently. So you can imagine it would start cutting down at the bottom of this valley. But as I mentioned before, rain, heavy rain, is the #1 risk factor for landslides. So you also might see everything slide off the mountain and fill the valley up. And I would actually say this is more typical of what we see in the short term. But one of the interesting implications of this model is that over the long term, for this landscape to reach the state of continuous erosion and uplift where those two are balanced, you have to end up with a whole different shape from what it was before. The river has to be lower in elevation, so it's a lower gradient going towards the ocean. The slope has to be less steep. So you have to remove everything between that dashed line and the new surface over a period of a long period. That's a pretty dramatic change for that landscape. So there are some implications from this model that are actually a bit non-intuitive, and some of these things I think, yeah, they're an active area of debate amongst my colleagues right now. One is that lots of rain by itself is not actually the risk factor we're worried about. It's when the rain is unusual, when this is something that the landscape has not come to equilibrium on. Another is that rock strength, actually we don't expect to be a big driver for landslide rate. If you have stronger rock, then this equilibrium model would predict that the slopes will be taller and steeper, and so they'll actually fail at a similar rate. So interesting implications that can come out of this sort of scientific thinking on this. Now my background picture here is from Wrangell, from a landslide that happened in 2023. That's an American football field for scale. If we zoom in over here, we can get some sense of what this event was like. You can see it covered the road here. It just missed this house. Unfortunately, there was another house. I don't know if I can do this. There we go. There was another house right down in this area, and it was destroyed by the landslide, and everyone in it died. It was a family died there. So it's a really devastating event. Now, this is one of actually 4 deadly landslides, all in southeast Alaska, that have happened over the last decade. And so this has understandably drawn a lot of attention, and there's a lot of effort going on to try to figure out how do we address this hazard. Oops. Another site that's drawn quite a lot of attention is Barry Arm in Prince William Sound. And this is a very different landslide situation. So here we have a very slow landslide, a landslide that in some years it moves several hundred feet, or around 100 feet in a year. Most years it moves a lot less. By itself, that slow motion is not really a problem. There's no road there that's getting destroyed or anything like that. But the concern is it could fail abruptly. And if it did that, it could produce a very large tsunami that might impact the city of Whittier. If you really start prying into the details of the impacts this could have, they become very large. There are cruise ships with thousands of people on board that go quite close to here. Some with over 100 people that come right up into this area. Much of Alaska's internet actually comes into Whittier. It's a major rail port for us. It's an important tourist port. So this particular landslide could have a lot of impacts. Now, let's take a moment to try to understand that situation using this equilibrium model. First of all, we have to change it a bit and put a glacier in there. A little bit different on the bottom. Same idea, glacier erosion. You have landslides up above the glacier that bring stuff down, and then the glacier transports that away. Now, if you change the situation by warming it up, not only do you get maybe more precipitation, but you also lose your glacier. And so you have this really steep lower slope. And if you look at that and you think, that looks a little bit sketchy and unstable, that's good intuition there. You don't want this really steep slope right down at the bottom. Now, what happens most of the time is that you get shallow landslides and they just kind of carve off the slope and make it less steep. They dump stuff at the bottom, carve away up at the top. This happens especially through rockfalls, which is one type of shallow landslide. But that isn't always what happens. Sometimes you get a failure that happens much deeper and you get a deep-seated rotational landslide. And again, this is not really a concern by itself. This is what has happened at Barry Arm, and most of the time these creep down, they make the slope less steep by rotating like that, and they eventually find a happy place and they sit there potentially for thousands of years. But in other cases, they don't. They fail abruptly and they go shooting off into the valley below, and they can go 100 miles an hour for many miles. They can be a really, really huge disaster and generate tsunamis, among other things. So that's the concern in this case. Just to show you what an event like that looks like in reality, so we have an example of a slow landslide. I keep trying to look at the screen and then navigate my mouse, it doesn't work. But right here, there's a slow landslide. This kind of arc here is that kind of steep crack up at the top of the landslide, so right here. In early August 2021, during a big rain event, this suddenly failed. It had been creeping along, maybe just even some of the time just sitting there for 100 years, and it failed. And when that happened, it went down, it banked off the far side of the valley, swept down, and actually most of the landslide mass is right here. Fortunately, my magic little football field just floated right up out of it. But there's probably over 100 feet of boulders in this area. The little lakes that were there, they're very small, but they formed this big tsunami that swept away the forest for this huge area down here. So quite a dramatic event. That's certainly not the only case. This is actually the tsunami that got me started looking at this stuff. I came from the tsunami world. Oops. This landslide and tsunami happened in 2015. The highest point that the tsunami reached up the shore was 630 feet. And then just last year in August, there was a tsunami at Pedersen Lagoon that the highest point it reached was over 200 feet up the slope. And these were generated by these same sorts of landslides. If you look across recent history, we actually see what might be the signature of climate change in this. There is a whole bunch of these events that have happened recently, very few going into the past. Now, we can talk about some of the ones I've left off here, but if we look exclusively at the ones that reflect that equilibrium process next to a glacier, they appear to be all really recent. I'm sure we've missed a few, especially of the smaller ones in the past, but because the traces these leave are so obvious, we actually think this is a fairly complete list here. Okay, so I've talked a little bit about two very different hazards, right? The shallow landslides that are happening quite frequently down in southeast, this potential for a huge deep-seated landslide that could generate a tsunami. Now, how would we actually go about comparing these and deciding how our agencies are dedicating effort to both of these? Is there one that's more important than the other? If you ask which one's most likely, it's very clearly the one on the left. If you ask which one's worse, it's very clearly the one on the right. So how do you deal with that? I think one way to think of this is with a graph like this, where you have on one axis, you think about how bad is something that arises, and on the other, how likely. And so in this just very cartoonish example, I'm imagining something where there's a range of possibilities here that are not that bad. And that's one possible outcome should one of these, whatever this hypothetical event happen. There are maybe some that are pretty bad. This is maybe people are dying, there's damage to infrastructure and so on. There's some that are really, really bad. And then there might be even some that we really don't even want to talk about. They're unlikely, but boy, if they happen, that would be really horrendous. Now, something that looks like this, very different than something that looks like this, right? Maybe most scenarios are okay, and only a few are just somewhat bad. So we can kind of think, things vary a lot in this space. How would we actually address that? And so I'm someone who likes drawing pictures, so try to think things through. So I'm going to spend quite a bit of time on this particular little graph. I'm going to use a little bit more technical terms on the vertical. Instead of just how likely, I'm saying probability. So that's the likelihood of something happening. On the x-axis, consequence, how bad is it basically? And so maybe if we look at all landslides that happen, shallow landslides that happen in Alaska, things like the Wrangell landslide in 2023, we might expect it to be quite high on this graph because they seem to happen a lot. It's fairly likely, but maybe not the worst consequence, so a little bit to the left. So they're going to be kind of in the upper left of this graph. Now, to really do this right, we want to put some numbers on here. So we could look at probability on a per year basis. What are the chances that something happens in a given year? And we could look at consequence. I'm suggesting a couple different things. This is kind of what goes into the headline of the newspaper, right? How many people died or how much did it cost? It's not a total coincidence, the alignment between these two. Notice I have one person dying lined up with $10 million of damage. $10 million is what is referred to as the statistical value of a human life. It is used in policy making to try to figure out how much it's worth investing in reducing the death toll of a given situation. So imagine you're changing the curvature of a huge freeway. It's going to cost you $100 million, and the only benefit it's going to have is it's going to save a few lives. How do you balance those things? It's difficult. So people do this. They actually go through and they have a complex procedure to create that equivalence. I'll also note that anytime you see a scientist show you a graph where it's like this, where it's called a logarithmic graph, where it's like a factor of 10 different on each axis there, it probably means they're going to be doing a lot of hand waving. They don't really have very specific ideas or data to constrain things really tightly. And that applies here. I'm going to be talking about this in very general terms. And by using these kind of graphs, I can still put something up there without feeling like I need to do more work to pin the numbers down. So, okay, if we throw our shallow landslides back up there, happening every few years, it's usually a few people dying in those. So actually that kind of works pretty well on the graph as I've drawn it here. Now, what about Barry Arm? Where would that plot in here? We can kind of speculate about what the cost would be, in a general sense, probabilistically how many people might die or how many millions of dollars of damage, and we can put it out here, but it's really hard to say what would the probability be. I've just smeared it across like a range that's kind of uselessly wide here. In order to narrow that down, what we would want is to have a bunch of places that looked like Barry, and we would want to sit and watch them for a while and see how many of them failed, right? And we could say, well, maybe then Barry Arm's going to behave similarly. So this is one of the things I've been doing, and I've been looking all over Alaska for different landslides that are deep-seated landslides, and in particular here, these are ones that are creeping. So there's this slow motion, that sort of motion that might lead to sudden catastrophic failure. There are a lot of them, but some of these are not very similar to Barry at all, so I'm going to start trimming it down a little bit here. So these are ones that are creeping along relatively quickly, and I use the term I use actually in my inventory is they are obviously creeping. And that means that I can spot them in pretty much any satellite imagery I look at. This is still a diversity of places that has some really different sites from Barry Arm, so I'm going to trim it down a little bit more and say I only want to look at sites that are next to, or at least were recently next to glaciers, and where I don't think permafrost was a factor. So if I don't think permafrost is a factor, it basically cuts out much of the state. It turns out these are, these two things lead the same direction pretty quickly. So now I have a set of places, 84 different sites that look kind of like Barry. Barry's on the list. It's one of the dots in there. Now let's watch this for a while. Now you notice in the title it says since 2012. So it's only recently that we have a huge amount of satellite data, so we can actually have some confidence that we're seeing a lot of what's happening out there. I won't say I've spotted every one by any means. I still keep finding new ones, but it's a fairly complete set. So how many of these have failed since 2012? Well, it turns out 5 of them have failed catastrophically on a scale that's big enough that if it happened at Barry Arm, it would create a tsunami of some sort anyway. So you could do some really simple math here, and you get a probability per year, 0.5% chance per year. Now there's better statistics you could do with the same numbers. You can use Bayesian statistics and stuff, but it really doesn't matter a whole lot because the data isn't quite good enough for the different statistical approaches to give you meaningfully different results. And one of the things that I think is an important weakness of this data, I want to point out right away, and it kind of shows up if we actually plot the years that these different events happen. So I picked all the events since 2012. 2 of them happened last year. That's a remarkable coincidence that 2 of them would happen in the most recent year. And you'll recall I showed you this graph before that shows that a lot of this stuff is happening only in the most recent decades. So my suspicion is that this assumption that looking towards even the very recent past is a good way of predicting the future is going to underestimate that probability. But we still have a starting point. And so we can take that really big blurry spot and we say, okay, maybe it's somewhere 1%-ish or a little bit less than that. I still don't really like my dot here. I kind of want to smear it out a little bit across a range of scenarios because, really some of these events are not going to lead to our most horrific consequences. But these are all consequential events I'm looking at. All right, so we now have 2 splotches on this graph. Does this actually tell us anything useful about how to compare these? What kind of a metric could we use to decide whether one part of this graph is more important than another? One way to look at this is to think very much like an economist. And you say, okay, let's say we had something that costs us $10 million happen once every 100 years. Well, you can figure out how much that's going to cost you on average each year, and it turns out it's exactly the same as something that happens once every 10,000 years but costs you $1 billion. So you could say, well, maybe these are kind of the same. And in fact, everything along a diagonal line, we could say is the same, and actually that applies for other diagonal lines. And so this gives us a basis. It would say well, maybe actually Barry's a little bit lower priority than these, the broad category of Alaska shallow landslides, although they're both kind of comparable. Maybe that means it's kind of a good thing that, that our agencies have dedicated resources to both of these. They're actually kind of similar hazards when you start looking at this. This concept of bringing probability and consequence together and trying to understand them collectively is what we would technically call risk. I mean, there's obviously a colloquial definition. It's not too far from this, but this would be kind of getting to a more technical definition. Some process by which you combine these 2 things. So when you identify something like this, then what do you do about it? How do you actually address these hazards? And we can actually see some of the actions that are going on here. There's various mapping and weather monitoring stuff going on in Southeast Alaska. At Barry, we have a variety of different efforts, including integrating with the National Tsunami Warning Center. And the goal of these is not to make them less likely. We don't really have a way of making these events less likely. You can ask afterwards. I can tell you about sci-fi scenarios where we would, but mostly we can't control their likelihood. What we're doing is we're trying to reduce the consequence. So we're moving them to the left. We'd like to move them down, but much easier is to move them to the left. So here's an example. This is a very recently published hazard map from Haynes showing some of the areas at risk. So this might give someone information about whatever development that they might want to do, or it might help DOT plan for response to damage to roads, that sort of thing. Now, I would say that nothing I've said here says these are definitely important to look at, but I'd note that I come from kind of a tsunami background, so I follow the tsunami hazard stuff in Alaska. And if we plot up some of the tsunami scenarios that we put quite a bit of effort into addressing, this is where they plot. So this is, if you follow the news, about a year ago, there was a bunch of news about the way they recognize that Ship Creek up in Anchorage actually is at some risk from tsunamis. So that ends up plotting pretty low down because it has to be a combination of these infrequent earthquakes and a high tide. I've looked very closely at our our tsunami scenario for Soldovia. It's actually, I believe, the same one here. And there are some reasons to think this is an extremely low probability event that is mapped on our standard tsunami hazard maps. So these, if you imagine those diagonal lines, look a little bit lower priority than things like Barry Arm and shallow landslides. So, maybe that's evidence that at least we're not overreacting to these landslides. Okay, so that was a little journey down science road. Have I now shown you that we as humans have something that clearly sets us head and shoulders above the bears for dealing with hazards? And I would argue that I have not, because what I've shown you is that as a scientist, I can keep myself entertained very easily. But I haven't shown you that that actually benefits anyone. And the example of the subduction zone earthquakes I gave earlier, I mean, plenty of people did lots of this kind of work, but the benefits were a bit equivocal at the end of that. And so I think that it's a bit questionable anyway. Now I think we probably can maybe finally answer the question posed by the picture, though. Bear trying to decide between the salmon and the probabilistic hazard map. You can call bear a lot of things, but don't call it late for dinner. I think it's going to go for the salmon. Okay, so I want to give you a little roadmap for the rest of this talk, just because it gets a little, I'm going to jump through a few different concepts. I think they tie together, but it might be a little confusing. I'm going to talk about a few examples of where we actually successfully use science to mitigate hazards, because there are some out there. I'm going to talk at some length about the things that scare me the most in Alaska. I'm going to leave Homer out initially. We'll get there. And I'm going to talk about how culture interacts with quantified risks. So that graph that I showed, how does culture actually come into play on that graph? Then I will talk about Homer. And finally, I have this little note at the end about jurisdiction. So you can wonder, where does that come from? Okay, so how do we actually use science successfully? I think the National Weather Service is a great example. They communicate modeled results for what kind of weather might be coming. And they communicate that very broadly. They provide it in a lot of different forms. Society actually picks up that information and whether it's on the Weather Channel or if you go to windy.com or something like that, they're translating that into something that's really accessible to a lot of people. It's probabilistic. It actually quantifies the likelihood that something will happen. And as frustrating as it is to get a 50% chance of rain forecast, that's a lot better than, I don't know, some weather forecaster is worried it might rain tomorrow. Like, having that number, I think, is really key to making it work. Something that falls a little bit closer to our subject at hand here is in earthquake hazard mitigation. So this was damage from the earthquake in 2024 in Taiwan. You can see there's clearly a problem with this building, but it's actually pretty darn impressive that despite the fact that maybe like a geotechnical engineer mischaracterized the material under the building and it started tipping, it still didn't break apart. Now you can see they went and put some I-beams there to make sure it doesn't finish its tilting job. So this was a huge earthquake, a devastating earthquake in a densely populated area, and I think 17 or 18 people died, which is tragic that those people died, but that is very impressive. Like, this is a pretty clear success story for hazard mitigation, and a lot of this has to do with a history of very carefully assessing the risk of earthquakes in Taiwan, especially in the wake of the Chi-Chi earthquake in 1999, and using that to inform building codes so that people built buildings that were able to survive this earthquake that happened. Now, I think this is also, so talking about how earthquake assessments translate through building codes to societal benefit, it's also a good example because this doesn't always work. And I think this comes back to this topic of culture. Culture includes a lot of really wonderful things that we all love. It also includes corruption and inequality and these sorts of things. And in Turkey, we got to see a just horrific example of this playing out. We, for a long time, understood very, very high seismic hazard in Turkey. They even developed building codes based on these. But builders were often not very careful to implement those. They could, and it was easy to bribe their way out of building inspections and stuff, and over 50,000 people died. Okay, so I showed you these couple examples of landslide hazards in Alaska, and I showed you this map, which is kind of the start of a hint that I've been thinking about this stuff quite a bit and doing a lot of mapping. So this is actually a figure I made this afternoon instead of practicing my talk more, which I probably should have done. This is aiming towards something I'll go into a paper I'm working on. So I've been doing a lot of mapping landslide activity in Alaska. And so this means I look at a lot of different places and I stumble across places where I'm like, whoa, this looks really scary. We have the coincidence between some sort of signs of landslide hazard and where people are. And so I'm going to give you a little whirlwind tour of some of those places. Start right here, right by Anchorage. Anchorage is in the lower left there. These different blobs on the landscape are all landslides that I've mapped. The red ones are the fastest moving slow landslides, so creeping landslides, but they're moving at this obvious rate. Yellow is kind of intermediate, where they're moving a bit. Green means I can see evidence they've moved at some point, but I haven't found any evidence they're moving right now. And then these blue ones are past catastrophic landslides, and these are all quite old, probably thousands of years old. For the person I was talking to about geocaching, this is one spot I would send people. But the one that really worries me here is this instability here, which is a big, slow landslide that is directly above Eklutna Lake. So we can imagine this is the sort of situation where this could fail catastrophically. It would then go right into Eklutna Lake. Downstream of that, you have all of the you have all sorts of infrastructure. You've got fiber optic internet, the highway, rail, power, all of these things right there. You also have the village of Eklutna. When I talked to them about this, they said, oh yeah, that makes sense. We have a story that our village will be destroyed by a tsunami. And we always thought it would come from the ocean, but there's no reason it wouldn't come from the lake. If you go up here, you actually see cracks in the ground, cracks in the tundra from recent motion. And so that's why I got that yellow color instead of just being green on my map. So where would that be on this map? I would put it way out here because the potential impacts are really extreme. However, the level of activity drops it in probability relative to something like Barry Arm. Here's a place that a part of the state that I've actually never been. I think a lot of people maybe don't get out to Nelson Island, but they happen to have a bunch of very active landslides as neighbors. These landslides are directly above the water. Big saving grace here is the water's very shallow, which really limits the size of a tsunami that could happen here. But no one's actually gone through the exercise of modeling the tsunami to try to figure that out. So I would guess at putting that risk somewhere in this area, but we really need more work on that. Glacier View is an area I've spent quite a bit of time recently. They happen to be a hot spot for landslide activity. I mentioned the way these light blue are ancient landslides. Some of them are also not that ancient, but they're small. But these dark blue ones, those are both recent and large landslides. And this is really a hot spot throughout the state, and we have a very active conversation going on up there. We actually have been getting together with locals, bringing locals and scientists together with agency folks. Sorry, I didn't mean to click quite so fast there, but anyway, I might put that one in this area. And there's a lot that we could do, I think, to start reducing the risk in that site. So here's one that's a little bit different. Mount Fairweather is fortunately very far from people because there's a lot going on. You can see all these gigantic blue blotches. These are enormous recent landslides. That one on the right there, Lamplugh landslide in 2016, I think it went about 4 miles, spreading down the glacier. Now the concern I have here is that when you have a huge mountain like Mount Fairweather, this is a picture I took of it from the beach, from the ocean shore, there's some thought that the way that these mountains stop growing is that the whole top falls off. And there's some evidence that may be something that's increasing with probability with climate change. So the possibility exists for not a landslide that's on a scale that's far larger than what we usually think about, failing here and actually flowing into the North Pacific. It could endanger ports all around the Pacific Ocean. So that's something that I think is actually fairly unlikely, but the consequence could be so immense that we might want to think about trying to study it a little. This is probably the place that has me most freaked out right now is Portage Lake, especially these two instabilities here right up near just right next to the glacier. These, if they failed, would almost certainly create a significant tsunami. and there's a tremendous amount of infrastructure around the lake. The visitor center being very notable, maybe the most vulnerable bit of infrastructure, but it's also, again, fiber optic internet, rail lines, highway, power lines. So that's another view of those unstable masses. We've done some preliminary modeling here. This is work by Pat Lynette. I thought I had his name written there, and somehow it's not there. But he's at the University of Southern California. And this is all very preliminary work still. But what we see in here is that though the tsunami kind of mellows out in the middle of the lake, it sweeps right across and actually concentrates somewhat where the visitor center is. And this is somewhat of a mid-range estimate. The largest possible tsunamis here are not, I mean, it's pretty much impossible to figure out what the largest possible is, but very reasonable larger tsunamis would be a much higher impact. So this one actually, I think, slips up off to the right substantially here. Now, one other one that's got me quite worried, I just actually had a long conversation with an oil company working up on the North Slope, is up at Adigan Pass, which is this black line here is the highway through the Brooks Range, and so the high point, Adigan Pass, is right here. So way up north, and it turns out there's a lot of activity up here. Now, down at the bottom of this screen, there's one that is actually pretty well studied. This is called Frozen Debris Lobe A, and this little animation, you can see it flowing in there. I'll click it a couple times. And so you'll also see that the road changes position in there. So the road has actually run away from this landslide. So that gives you some sense that this landslide is big enough that they didn't think they could just push it out of the way. They actually had to move the road. And right near the new position of the road, this line here is the pipeline. And these shear the subsurface down to many feet below the surface. So even though the pipeline is buried there, it would be in danger if this slides across the road. So this has been known for a little while, but what wasn't really known until the mapping I was doing is that there's this huge cluster of really active slopes up near the pass. And so I'll just point to one of them here. And so, again, this is hard to look at the screen, but watch right over here where my mouse is, and you'll see a piece of the mountain come loose and slide down over the course of years. Now that one seems to be working itself out okay, but it's a sign that this mountain is responding to warming in ways that we don't fully understand. And I think it's a very serious risk that there might be other parts that would let loose. And there are a lot of other things that are potentially harmful here. So I actually put this one at way out here up to the right. Now, fortunately, this one is not so much a death toll kind of situation. This is more about economic impacts. So that's the only bright spot in plotting that there. But I do think there's actually a really high probability of the pipeline corridor being severed through the Brooks Range. And this is also relevant to the current conversations about a gas pipeline. If you're going to use that same corridor, that puts that gas pipeline at the same risk. So I could keep going here for quite a while. There are a lot of places that worry me in Alaska. Crew ink right across the water here. This is one of the challenging positions I put myself in, is knowing about a whole bunch of things and having absolutely not the capacity to really give them the attention they deserve. So if we look at these different scenarios, one thing I wanted to note is that you'll see similar kinds of mitigation measures come up on a lot of my slides. One is monitoring, looking for changes in activity. Mapping, this is the one that even without salmon bribes, people might raise some concerns about, but I do think it's an important part of the conversation. And also modeling of different scenarios that might come out. But I think one of the challenges here is I've made this big mess of points. I even talked a little bit earlier about how you might look at this in terms of risk, how you might consider both axes, both the probability and the consequence at the same time. But is that important? What is it that would actually be important? And so I was trying to figure out a way of answering this question, because it's ultimately a cultural question. It's what do we actually care about? What is our risk tolerance and such? I did some digging in, especially in the Norwegian and Swiss literature, and you don't need to try to figure out what's going on in these figures, but I did find examples where they actually used graphs that were something like that one I'm showing you. So if we take the Norwegians' take on risk, they would put most of this stuff in their high risk category. They're like, let's have a meeting with the president and start figuring this out category. And the rest of them fall into this medium category. Now, of course, that's somewhat, I've plotted the ones that worry me, and so that's kind of maybe, I have it, there's lots of places that are low risk, and they're just not things I've talked about today. One thing that's really interesting, though, this is the Norwegian take. Here's the Swiss take. It's a really different graph. They have a very different set of prioritizations. And I think this really helps see how they're a lot more risk tolerant, for one thing, but how this is a cultural artifact, that the way that we classify what is an important risk or not, that is a cultural artifact. Now, I would say this isn't emergent from necessarily a very broad part of the culture in Norway and Switzerland. This is a highly technical field that a few professionals really engage with. So I won't say it represents everyone in the country by any means, but it does give you some sense that there are huge variations in this. If we look at that, what are the diagonal lines? This is this kind of economic idea. You can call this like a least cost or anyway, there are different ways you can look at this, but this is sort of constant financial cost on one of these. That matches the Norwegian picture really well. And I suspect this is somewhat because this is actually quite a modern development in Norway. It's only in the last 20 years that they've really tackled this question. So what about Switzerland? Well, one way that I think about this is there's a certain logic to curving this line upward. That basically, at some point, you say, that scenario is so unlikely, like fair weather down there, such an unlikely scenario that maybe we just won't worry about that. And you're probably going to be okay, right? Because it's probably not going to happen. And I think that's a very intuitive way of thinking about risk, that we would say, these really unlikely things, we won't worry about those so much. Now, I think there's another way you can think about this, and this is a sort of emerging idea, and if you do a Google search for the phrase robust decision making, it refers to this. And so the idea there is that actually you want to emphasize those most disastrous scenarios because those are the ones that completely change the course of history, that can destroy your communities, this sort of thing. You might even preferentially emphasize those over things that are going to, on average, cost you more, but society has the capacity to adapt to. So these are different takes on this. And I think that intuitive one, you could say it's somewhat similar to the way the Swiss are looking at it. I tend to lean towards this more robust perspective. It might be partly because I just get really excited by just giant, dramatic, huge disasters. But I do think that when we look at how the most horrific disasters play out, it's so terrible in terms of our, the fabric of our society. I think about being in communities in Sumatra where I mentioned that one town where everyone survived. There was some where the survival rate was down under 5%, sometimes as low as 1% of community members survived the tsunami. So when you're looking at that sort of thing, it's not just counting up the bodies that matters. This is also completely destroying a whole culture, and I think that adds weight to it. So for that reason, I would argue for something like this sort of logic. Okay, let's talk about Homer just a little. I am getting close to the end here. Not too many people have fallen asleep, hopefully. So I'm gonna talk about two different hazards. One is the canyons up above town, and the way that they can shed these debris flows down towards where people live. And the other is the Bluff Point landslide. So this huge landslide, it happened around 300 BC or so, where the bluff top slid down into the ocean. It's moving slowly today. And the concern here is that this could expand retrogressively. So a new piece behind it could fail and join the part down below. And there are very good reasons to think that might happen. In order to grapple with these, I'm going to add one more layer of complexity and sort of technical detail to my risk map, because I know you guys were hoping for that. You were like, that was too simple what you were showing before. Oh yeah, I was just going to note, I showed this hazard map at my presentation last year, but so what I'm talking about for the canyon landslides is like this stuff out east end, and Bluff Point is out here to the west of town. But so instead of showing you just a blotch like this, I'm going to talk about a line on this plot. Because there is a wide range of possible outcomes with different probabilities. And in a lot of cases, if you were to look at the distribution of outcomes for many different hazards, you would find they would have some shape like this, where they are going to decrease. So as you get to more severity, the probability drops. And so you have this trade-off, even within one narrow classification of probability and consequence. Now, I think Bluff Point is actually an interesting example where it's not like that, where there are a lot of scenarios that basically have no impact, including some failure scenarios. But when we actually start talking about an impact, it very quickly becomes severe. There's not much difference in probability between someone loses their outbuilding next to the bluff, and you've actually severed the highway and the natural gas pipeline and had these long-term consequences. And so for this reason, I think we end up with a very different curve, something like this. And you can actually add these together, and you can get kind of an overall hazard curve for Homer. You could add other landslide scenarios in here. I actually don't think with my kind of log graphs, which help kind of make this a very vague, hand-wavy thing. I don't think you'd see much change if you added in other ones, because I think they're low enough probability that they wouldn't shift that line much. And really, so we can look at it as a total line. If I'm, to try to capture the idea that I really don't know exactly where that line is, it could be anywhere in here. If you want a new word for the day, that's the epistemological uncertainty. This is the, I don't actually know where the line is. But we're going to ignore that for the moment. If you were to think of this more in terms of my fuzzy blobs from the previous plots, you might put a couple different blobs up here. One for Bluff Point, that's down to the right, and one for the shallow landslides up to the left. So how would these stack up in those different risk matrices? So Norway would put them, almost all these scenarios in their high risk category. The Swiss is kind of interesting. So if you really take this at face value, what they're saying is they're most worried about the highest probability but relatively low consequence Bluff Point scenarios, and a little bit about the worst possible canyon landslides. But they're going to mostly ignore the run-of-the-mill canyon landslides and the really unlikely Bluff Point scenarios. So this is something, I guess, do I put mine on there? Yeah, sure, there it is. So yeah, if you ask me, I'd say maybe we want to put a little more emphasis on that Bluff Point scenario. And I think this gets to what for me feels like a pretty deep point that I feel like I'm struggling to communicate, and I hope you guys are bearing with me some here. But this is a very, this question of whether we are actually going to worry about these low probability things, that's really getting furthest from the way that bear behaved, right? The bear, I don't know if we were to draw the bear's line, it's probably going to, maybe it would tilt down over here, but it's just going to flatten out. At some point, the bear is just yeah, I don't know. These things don't happen very often. I don't have any time to think about that. And so it's this question, if we really want to look at the maximum power that science can provide to benefit society, it's really when you start getting out towards this lower right end, where that's something we can't just address with our kind of intuitive take on things. One interesting, I threw this slide in at the last minute, so I forgot about it, but one interesting example, I think, of addressing that kind of lower right corner is this organization in Soldovia that looks at oil spill hazards, and I'm involved with them. And so they formed after the 1989 oil spill, and they're a nonprofit run by community members, and they're still there. They're still operating today. And so, yeah, that's been 40-ish years. Are we there? Not quite, but 35. This is an organization that easily could go through 100 years of operation and never be used for its intended purpose, right? Because it's preparing for an Exxon Valdez style oil spill, a really horrific disaster in Lower Cook Inlet. And that hopefully will not happen. And so it would be easy, it would be intuitive to say, well, do we have this organization that may provide zero benefit through this incredible cultural effort over 100 years? And I would point back to the village of Langi in Sumatra, where they held on to this information. Actually, probably was around 100 years since the most recent tsunami in that village. They held on to that information, and it paid off in spades when that finally came around. So I think that it's a very difficult thing how you actually address these low probability, high consequence events. But if you can manage it, it can work out well. Now, as my last point, I just want to bring up the question of jurisdiction, because I'm putting different things on here, right? So shallow landslides throughout Alaska kind of define that as Alaska is the scale that we're talking about here. Barry Arm is more localized. There's certainly Alaska-wide impacts, but it's this localized hazard. And I think if we look in this space, things really vary when we think about hazards in their jurisdiction. If you look at just a car accident for yourself, you might die, right? So the maximum possible impact is one person. And I think this is 1 year. Yeah, I looked up the typical death rate from driving, and it's around 1 in 10,000 per year for an individual. So it's definitely in that low risk category. And so I think it's really unlikely that Congress would pass a law that addresses just you particularly in order to reduce that hazard. But if you look at car accidents in general for the United States, this is where they plot. So a very different place, well out into the high risk zone there. And so that shows how it really matters what the box is that you put around one of these problems. And I think there are some boxes that are even bigger than our whole country. And climate change, I think, is a very interesting problem. It's something that we kind of need to look at on this global scale. So this jurisdiction becomes global. And it's very difficult to talk about that without having that kind of global level perspective. And maybe you can think of some people who think we shouldn't be thinking on that large of a jurisdiction. Okay, thank you very much. That's what I want to say today. I really appreciate you hanging with me.